Assalamu alaikum wa rahmatullah. Welcome back. This is Dr. Muhammad Saad, and we are continuing our lectures on random signal theory. We are in chapter 3, which is entitled Discrete Random Variables. In the previous lecture, we talked about the idea of the discrete random variable, what it is, how we can express it, and we also talked about the probability mass function. So the probability mass function was a function that was denoted by f of x, small f of x. This was the probability mass function. So it's a lowercase letter f of x, which indicates the probabilities of the different values of a random variable. So f of x was by definition the probability that our variable x is equal to some value x. Again, so f of 0 for this kind of random variable example, f of 0 is the probability that x equals to 0, which is this value 0.6561. For example, f of 3, little f of 3, here is the probability that the variable x is equal to 3, which is this value 0.0036. So what you see here, this function is called the probability mass function. It's a function that we can also draw, and it represents the different probabilities of the different values of a discrete random variable. Each value has a probability. Each value has a probability, and these probabilities together, we can think of them as a function, which we call the probability mass function. So we talked about that in the previous video, in the previous lecture. Today, we would like to introduce a new concept. We are still having a discrete random variable, but we define a new function which we use for which we use the uppercase F, so the capital F of x. The capital F of x is known as the cumulative distribution function. Now, what is the definition of the cumulative distribution function? It's the probability that our variable is less than or equal to some value x. So the probability mass function little f of x was the probability that x equals to a value here. So as you see the different values, this was little f of 0. This value was little f of 1. Little f of 2, this is the probability mass function. But the cumulative distribution function, for which we use the uppercase f, so the large f of x, the capital F of x, it really means it is defined as the probability that our variable is less than or equal to some value x. For example, if we have a variable x, what is f of 2? It's the probability that x is less than or equal to 2. So what's the probability that x is 2 or less? Not exactly equal to 2, but 2 or less. Since less than or equal to x, less than or equal to value x, it would be a summation over all values of the variable which are less than or equal to x. So we sum up all the probabilities. You will see an example or multiple examples in which we do that. I think the best thing to avoid confusion here and to avoid the dryness of just looking at the definition, let's look at an example right away. So in this example, we will be building up the cumulative distribution function slowly. So let's look at this example here, because the beginning of this example is really using our information on chapter 2 to construct the variable. Once we construct the variable, we continue and apply the cumulative distribution. Now, what is this function? What is this example? Sorry. What is this example about? Suppose that a day's production of 850 manufactured parts contains 50 parts that do not conform to customer requirements. So we have 850 components of a certain component, parts or components of a certain manufactured part, and those 850 contain 50 that are defective, like the example that we solved in the tutorial, but using different numbers. So we have 850 manufactured components, like pens, pencils, markers, whatever, cars, any components or any manufactured parts, 850 of them in a pile or in a box. Among them are 50 that are defective, which means automatically 800 exactly are okay. So the 800 of them are okay and 50 are defective. Now, what's the deal here? We define a variable x. First of all, 2 parts are selected at random, just as in the tutorial question. You are selecting 2 parts at random without replacement. So you go ahead and you choose one of them at random, and then you choose the second one at random. However, we have to define a variable x. For this question to be part of this chapter, we have to define a variable x. So the question itself says let random variable x equal to the number of defective parts in the sample that you choose. So we have 850. Again, we have 850 manufactured components in a box or in a pile mixed up together. 50 of them are defective and 800 are okay. You go ahead, you close your eyes, and you choose 2 of them without replacement. So the first one, and you put it on the side, and then you go and choose the second one at random. Now we define a variable x, which is equal to the number of defective parts in the sample of 2 that you have chosen. The number of defective of them, the number of defective parts of your 2 is equal to the variable x, is defined as the variable x. Now, to begin with, of course, the question says, what is the cumulative distribution function of that variable x? So for this variable x, what is the cumulative distribution function? Sorry, the cumulative distribution function, capital F of x. Now, to get the cumulative distribution function, first of all, we have to express x in our standard form. So we're used to expressing discrete random variables in this form. So x is 0 or 1 or 2 and so on, and each value is coming with a probability. Now for this example, the variable was not given explicitly, but we are given the experiment that leads to the variable. So we have to calculate basically the different values of the variable. Let's look at my own notes here, which contains the solution. So in summary, we have 850 parts, 50 of them are defective, and 800 are okay. We choose 2 without replacement, and our variable x is defined as the number of defective parts in your sample of 2. What are the different values for x? Obviously 0 or 1 or 2. X is 0 if both if your sample consists of 2 items that are both non-defective, that are both okay. In that case, x is equal to 0. Again, what was the meaning of x? X was the number of defective parts in your sample, right? So x could be 0 in case both of them are not defective. So if both are okay, then x is equal to 0. X could also be 1 in case your sample contains one item that is defective and the other one that is okay. X could also be 2 in case both items that you have chosen are defective. So x is 0 or 1 or 2. Obviously, it cannot be 0. It does not make sense in this context because x is the number of defective parts in your sample, which cannot be negative, and it cannot be more than 2, so it cannot be 3 or 4. This again does not make sense because your sample has only 2 parts. So x, which is equal to the number of defective parts in the sample that you have chosen, is 0 or 1 or 2. Now, the remaining thing is the probabilities. What is the probability that x is 0? What's the probability that x is 1? What's the probability that x is 2? I mean, this could have been given in the question from the beginning, but this question really tells us about the experiment from which we have to derive x. So we have to get these probabilities by ourselves. So this is the first part of solving the question. Once we are done with this, once we are done with finding these probabilities, it means we are back in this chapter. So finding these probabilities is like a question on chapter 2. Once we find them and we have the random variable like this expressed in standard form, we are back in the chapter, and then we go ahead to calculate the cumulative distribution function. So let's focus on how we find the probabilities first. What's the probability that x is equal to 0? How can we get the probability that x is equal to 0? What's the meaning of x equal to 0? Both are not defective, or in other words, both are okay. So the probability that x is 0 is the same as the probability that both items that you have chosen are okay. What's the probability that both are okay? It means both of them are coming from the 800. So 800 over 850 times 799 over 849. If the first one is okay already, if the first one is okay, it means the remaining okay ones are 799. So that's the number of chances that are available for the second choice, for the second item, and then divided by 849 because the total is also 849 once we choose the first item. It's exactly the same as in the question that we have seen in the tutorial. So 800 over 850 times 799 over 849, multiplying these numbers will give us 0.886. So 0.886 is the probability that both items that you choose are okay. Since both are okay, it means 0 are defective, and this is the probability that x equals to 0. So we have the first probability. Now let's focus a little bit, because the probability that x equals to 1 has a small trick. What is the meaning of the probability that x equals to 1? Is it the probability that the first one is okay and the second one defective? Or is it the probability that the first one is defective and the second one okay? No, neither of those. The probability that x equals to 1 means the probability that one of your sample is defective and the other one is okay. One is defective and the other one is okay. That's why we have to add two things here. One defective and one okay means the first one defective and the second one okay, plus the first one okay and the second one defective. I mean, if you choose a sample of two items, how can you possibly get one of them defective and the other one okay? This could happen if the first one that you choose is defective and the second okay, or if the first one is okay and the second defective. Both of these cases lead to one defective and the other okay. This is the meaning of x equals to 1. Remember, x was the number of defective parts, just the number of defective parts, regardless of whether it was the first or the second. So that's why to calculate the probability that x is equal to 1 here, we have to add up two cases. The probability that the first is defective and the second one is okay. How can we get the probability that the first is defective and the second one okay? First is defective, it means it's coming from the 50. So 50 over 850. Now once we choose a defective item, what's the probability that the second one is also, given that the first one is defective? What is the probability that the second one is okay? It means okay, the second one is okay, it means it comes from the 800. Remember, if the first one is defective, then the 800 were not affected. So that's why for the second, we have 800 over 849 because the total is one less. After we choose the first one, the total becomes 849. But if the first one is defective, the second one, for it to be okay, it is chosen among 800 because the first one is coming from the 50 and the second one is coming from the 800. So 50 over 850 times 800 over 849. That's the probability that the first is defective and the second okay. Is that it? Is this the probability that x equals to 1? No, we have to add the opposite. The probability that the first one is okay and the second one is defective here. First one okay means 800 over 850. And given that the first one is okay, the probability that the second is defective is 50 over 849. Again, the 50, because the 50 were not touched, the first one is coming from the 800, but the total is still 849. If we calculate these values and add up the two terms, it is 0.111. If you just want to compare the solution with what you see here on the slide, this is 2 times. It just happens that this term and this term are exactly the same. I just was keen to write it down like this because this is what it means. The first one defective and second one okay, plus first okay and second defective. But if you compare the numbers, 50 over 850, 800 over 849, it's here 50 over 850 and 800 over 849. So numerically, this term is exactly the same as that. That's why you see times 2 here. And the answer is 0.111. Finally, we have the easy case. What's the probability that x is equal to 2? X is equal to 2 means 2 items are defective. What's the probability that x equals to 2? It is the probability that both are defective. So the first one is defective with probability 50 over 850. Given that the first is defective, what's the probability that the second is also defective? 49 over 849. The first one is coming from the 50 and the second one is also coming from the 50. So we have 49 remaining at the second choice, 49 over the total of 849. Multiplying these two terms gives us 0.003. Exactly what you see here in the slide solution. 0.886, 0.111, and 0.003. Putting things together, we have our random variable here. X is 0 or 1 or 2. We were given the meaning of x. It's the number of defective parts. But after we have obtained the probabilities, we can just think of this as a random variable, forgetting about all these details. So the first part of solving this exercise was really using information from chapter 2, like our tutorial question. However, once we have the random variable, we can now forget about this and start with the random variable x is 0, 1, 2 with given probabilities. And now we need to get the cumulative distribution function. Let's focus together and concentrate so that we learn how to get the cumulative distribution function in case we have a discrete random variable. What was the definition of the cumulative distribution function, capital F of x? It was defined as the probability that our variable is less than or equal to value x. The probability that the variable x is less than or equal to value x. In other words, here since our variable is 0 or 1 or 2, let's start with a 0. What's the cumulative at 0? Capital F of 0. By definition here, it's the probability that the variable is less than or equal to 0. But 0 is the first possible value. Do we have any values for x less than 0? We don't. So the probability that x is less than or equal to 0 is the same as the probability of 0 itself, 0.886. So the first cumulative is always the first probability. Now, I will comment on the red sentences later or the red equations later, but let me move to the next point here. The cumulative at 1. What is capital F of 1? Let's just substitute here. Capital F of 1 is the probability that x is less than or equal to 1. What's the probability that x is less than or equal to 1? It's the probability of 0 plus the probability of the 1. So P0 plus P1, 0.886 plus 0.111, adding them together will give us 0.997. So did you notice something interesting here, or a nice observation? When we get the cumulative distribution function for a discrete variable, and this is our chapter's focus, the first cumulative value is the first probability. The second cumulative value is the first probability plus the second probability. I think you can guess that the third cumulative value is the first probability plus the second plus the third. And since we're adding probability, that's why we call it cumulative, additive, cumulative, like your cumulative GPA, which is the total GPA added over all the courses that you've taken in the university. Let's continue. What is the cumulative value? Capital F of 2. What's the cumulative value? Capital F of 2. Again, substitute in the definition. Capital F of 2 is the probability that the variable is less than or equal to 2. What's the probability that the variable x is less than or equal to 2? It's the probability of being 0 plus the probability of being 1 plus the probability of being 2. So P0 plus P1 plus P2. If you add up these probabilities, it's equal to 1. Because we're adding all of them, and the sum of all probabilities has to be 1. That's why the cumulative at the end is definitely equal to 1. So we obtained the cumulative function value at 0, the cumulative function value at 1, the cumulative function value at 2. But what about the values in between? Can we define the cumulative everywhere else? Yes, we can, but you will find that it's exactly the same, and that's why I have these red statements here, just to give you an example. We obtained the cumulative at 0, which is P0, 0.886, and we obtained the cumulative at 1, which is P0 plus P1, which is 0.997. Now, what about the cumulative at 0.5, for example? Or the cumulative at 0.6 or 0.2, any value between 0 and 1. What's the cumulative at 0.5? Let's just do it in a straightforward way. Let's substitute in the definition. The cumulative capital F of 0.5 is the probability that the variable x is less than or equal to 0.5. What's the probability that this variable is less than 0.5? What are the only values less than 0.5 or less than or equal to 0.5? It is the 0. So this is the same as the probability of 0, which is 0.886, which is the same as f of 0. If you want to get what's the cumulative function at 0.6, it's also P0. What's the cumulative at 0.9? It's also P0. So the cumulative at 0, the cumulative function value at 0 was the first probability, 0.886. And the cumulative function at any value for x between 0 and 1, before 1, until before 1. So from after 0 until before 1, like 0.5, 0.6, 0.7, 0.99, all these values, the cumulative has exactly the same value, 0.886. So if we need to express the cumulative function in a complete way, we say the cumulative function for x is equal to 0 for all values of x less than 0. By the way, f of 0 is the probability that x is less than or equal to 0, which is P0, 0.886. What about before 0? And what is the cumulative function at minus 1? Do we have any value less than 0? We don't have, which means a 0 probability. So for all x values less than 0, the cumulative is equal to 0 because we don't have any values, we don't have any probabilities. Now, what about the cumulative for all values, the cumulative f of x for all values of x greater than or equal to 0, yani starting from 0 but less than 1 and before 1? that cumulative function of x is equal to 0.886. Do you see f of 0 here is 0.886, but all values of x until before 1 also have a cumulative value of 0.886. So 0.886 is the cumulative function value for x greater than or equal to 0 and less than 1. What about starting from 1? X greater than or equal to 1 and less than 2. The cumulative is 0.997, which is the same as capital F of 1. Likewise, as using this argument, what is the cumulative function value, let's say at a value greater than 1 but before 2, like 1.3 or 1.4 or 1.15 or 1.99. What's the cumulative at 1.3? It's the probability, just substituting the probability that variable x is less than or equal to 1.3. What are the values less than 1.3? It is the 0 or the 1. So the probability that variable x is less than or equal to 1.3 is the probability that it is 0 plus the probability that it is 1, because these are the only two values, less than 1.3, less than or equal to 1.3. So adding up gives us 0.997. So again, the cumulative stays fixed, stays as it is from 1 until before 2. What about after 2? F of 3 or F of 4 or F of 5. F of 3, for example, capital F of 3 cumulative function value at 3. From the definition, the probability that the variable is less than or equal to 3. Now, 0 or 1 or 2 are the only values available less than 3. P0 plus P1 plus P2, which is 1. Just the same as the function value at 2. Again, putting everything together, the cumulative function value of x, the cumulative function of x, capital F of x, is 0 for x less than 0 because we start from 0. So before 0, the cumulative is just 0. From 0 until before 1, so starting from 0, greater than or equal to 0 and less than 1, the cumulative is 0.886, which is the first probability. From after 1, starting from 1 and before 2, so greater than or equal to 1 but less than 2, the cumulative function value is the first plus the second probability, 0.997. Now, greater than or equal to 2, for all values of x greater than or equal to 2, the cumulative has a value 1, which is the sum of all three probabilities. So analytically, this is the way we should express the cumulative value, and we can also draw it. As you notice, it's a piecewise continuous function, so that cumulative function x is fixed from 0 to 1, and then it goes to another value from 1 to 2, and then it goes to another value from after 2, and it stays. We can put things together by drawing the function. So again, on the x-axis, we have the variable values x, 0, 1, 2, and so on, and on the y-axis, we have the cumulative function, capital F of x. This time, how do we draw this function? Before 0, as you have seen, before x equal to 0, the cumulative function value is 0. So this green arrow going to minus infinity, for all these x values, the cumulative is equal to 0, but excluding the 0 itself. That's why we have an open circle, excluding the 0 itself. At 0, at x equal to 0, the cumulative goes to 0.886. Here, at x equal to 0, the cumulative becomes 886. Do you see this equal sign? At x equal to 0, we have a value 0.886. So we go to 0.886 and it stays fixed until before 1. It stays fixed until before here. From 0 to 1 until before 1, it stays the function, the cumulative function stays fixed, excluding the 1. That's why we have an open circle here. So here at 0, we had an open circle, and 0 itself, we have a closed circle, which means the function value at 0 is this and not that. But before 0, it was just 0. We have an open circle because at 1, we have a new value. We go up to 0.997 here. 0.997 is the function value at 1, the cumulative function value at 1, 0.997, and it stays fixed until before 2, open circle. At 2 itself, we go up to the new value, which is 1. The sum of all probabilities here, it's 1. At 2 onwards, we have a closed circle onwards until infinity. The cumulative function value is 1. So as you noticed, for any discrete variable x, the cumulative function, capital F of x, starts with 0. And then we go up at the first variable value 0, we go up at the second variable value, we go up at the third variable value, we go up. So at each variable value we jump because we add a new probability. In between, we always have a fixed value, and then we jump up at the next x value. At the end, it needs to be 1. It needs to be 1, obviously, because if we add everything, it's 1, never more than 1, and then we stay forever until infinity. So again, I talked about the cumulative, how to calculate the cumulative distribution function f of x in full detail, and we talked about a particular example in which the first half of the example applied information from chapter 2. Once we have the variable itself, we get the cumulative, and that's what we do in the discrete case. It's very easy. We have a discrete variable. We get the cumulative at 0 and 1 and 2. Cumulative at 0 and 1 and 2. First probability at 1, first plus second, at 2, first plus second plus third, and then in between, it stays fixed at the end. We can express it analytically in that way, or we can draw it in that way. So this finishes our discussion about the cumulative distribution functions. For a discrete random variable, what are the concepts that we have learned? We learned how to express the variable itself. This is the way we express a discrete random variable. We talked about the probability mass function, that little function f of x, and we talked about the cumulative distribution function, the capital function f of x. Now we would like to go to another concept, the mean value of a random variable and the variance of a random variable. So what is the mean value of a random variable? You know, we have a random variable here. Like in this case, x is 0 or 1 or 2, each one of them coming with a probability. So x is 0 or 1 or 2, depending on the experiment. If you do the experiment, we generate a value for x, and it could be 0 or 1 or 2. On average, this is the question. On average, what's the value for x? And this is what we call the mean value. So the mean value of a random variable, in other words, we also call it the expected value of a random variable. So the mean or the expected value, it reflects the average value of this random variable. How can we calculate the average, mean, or expected? All of these names are equivalent, and it is given the symbol expected value of x. E of x, E stands for expected value of x. We also give it the symbol mu here. So these are two alternative symbols for the mean or the expected value of a random variable, expected of x or mu. By definition, we add up all variable values multiplied by their probabilities. So the mean or expected value is a weighted sum. It's a summation over all variable values, the x value itself multiplied by its probability. So here in this case, what would be the mean value for x? The mean value for x would be 0 times 0.886 plus 1 times 0.111 plus 2 times 0.003. So we can think of these probabilities as weights, and the mean value is the x value times its probability plus x value times probability plus x value times probability. So if we do that for this example here, so we have 0 times 0.886 plus 1 times 0.111 plus 2 times 0.003. The answer is 0.117. I hope that you're listening to me. The answer is 0.117. So this variable, on average, yes, the variable itself has values 0, 1, or 2, but on average, on expectation, this variable has the value of 0.117. It's close to 0 because 0 has the highest probability. Now, this is what the mean value means. As you notice, we just obtained the expected value of x for this example, for this random variable. What was the mean value again? 0.117. Is 0.117 one of the actual variable values? No, it is something else, and it's not necessary that the mean or average value of x is one of the values. It could be something else. It could be something in between, because this is just an average value. Imagine that you take a course. If you take a course, you can get an A or a B plus or a B, right? So A means GPA 4, B plus means GPA 3.5, and B means GPA 3, and so on, 2.5 and 2. So these are the particular values of the GPA in a course, 4 or 3.5 or 3 or 2.5 and so on for a particular course. But if you calculate the average GPA for all the courses, it could be 3.71. Right? Is 3.71 something that you can get in a particular course? No, in a particular course, you can get 4 or 3.5, but if you calculate the average, it could be 3.9, it could be 3.3, 2.8, and so on. So the mean value the mean value or expected value of a random variable is not necessarily one of the possible values of the variable itself. It could be something in between. We will see some other examples. Now, so this is the mean value. Let me show an example here which will give you a better feel of what the mean value is. This is another random variable here, another random variable. Imagine that we throw a die, that we roll a die which has faces from 1 to 6, and then we define random variable x to be the number that you see on the face. So that random variable is obviously 1 or 2 or 3 or 4 or 5 or 6, and the probability of each one of them is 1 over 6 exactly, simply because the die is fair and each face has exactly the same probability. So from our previous knowledge, this x variable is 1 with probability 1 over 6, 2 with 1 over 6, and so on. All probabilities are the same, 1 over 6, and 6 is just the number of values that we have. So let's think of this as a random variable here. The probabilities are all the same. In this particular example, let's calculate the expected value of x that we also call mu. By definition, it was the summation of x times f of x. So summation over all values of x, x times f of x. So 1 times 1 over 6 plus 2 times 1 over 6 and so on, plus 3 times 1 over 6 plus at the end plus 6 times 1 over 6. Let's do a trick here. If we take 1 over 6 common, this is equivalent to 1 plus 2 plus 3 plus 6 divided by 6 now. So it looks like the average that you are used to. If you calculate the average of some numbers, you add up the numbers and then you divide by how many numbers you have. Now for a random variable, the average has different definitions because the probabilities could be different. However, in the special case that the probabilities are all the same, it goes back to the form that you're used to, 1 plus 2 plus 3 plus 4 plus 5 plus 6 divided by 6. But in general, if the probabilities are not the same, then the expected value, the average of a random variable, is calculated by adding up or doing the summation of the different variable values times their corresponding probabilities. Like in this example, 0 times 0.886 plus 1 times 0.111 plus 2 times 0.003. So this is the expected value of a random variable. Again, it's called expected value. It's called the mean value or the average of the random variable. In addition to the expected or mean, we also define something very important called the variance of the random variable. Now, the variance of the random variable, it's given the symbol v of x, variance of x. V of x, it's also called sigma square. Yes, the variance itself is called sigma square, simply because sigma is called the standard deviation. Maybe you heard about the standard deviation, but the variance is sigma square, which is the square of the standard deviation. Now, the variance of x, or sigma square, for random variable x, what is the definition of it? Let's look at the definition, and then I'll spend some time with you trying to explain the meaning of this definition. X is the variable. X is the variable. So if we take the x value, the variable value, and then we subtract the mean. Remember, mu was the mean. Mu was the average of the random variable. Again, is x a variable or a constant value or a number? No, x is a variable. It could be this or that, depending on the definition of the random variable x. However, mu is the expected value of the variable, which has a number. Like for this random variable, we calculated the expected value by adding up 0 times plus 1 times and so on, and it was 0.117. So this mu is a number. So what do you see inside the bracket here? Inside the bracket is the variable value minus its mean. Variable value minus its mean. Since this could be negative or positive, let's square it as by definition. So variable value minus mean squared, so that we get rid of the minus, the square of the difference between the variable value and the mean, and then average. That's why we see expected value outside, averaged over all x values. In other words, the variance of a random variable reflects how different are the different x value from the mean square. So the squares of the differences of the variable value and its mean averaged over all variable values. This is the meaning of the variance. Mathematically, the variance of x, that's also given the symbol sigma square. By definition, it's the expected value of x minus mu square. So what does it reflect again? It reflects the differences between the x values and the mean. So if our variable here, if our variable has values that are very different from each other, very different from the mean, it is expected that the variance has a large value. But if we have another variable in which the different variable values are closer to each other, like 0 and 0.01 and 0.02, these values are close to each other. If we calculate the variance using this definition, we're expecting the variance or sigma square to have a small value. So, putting things together, the mean or the expected value of x is an average value, so it reflects really the balance point. So if we have a variable here, let me show you a motivating example here, or an illustration, an analogy. This number line represents the different values of x. So we have a random variable x which has this possible value and this possible value and this possible value and so on. The length of the arrow represents the different probabilities. So the length of the arrows represents the different probabilities. If you think of this as a random variable and then you calculate the mean using this summation as we're used to, it would give you maybe a value here. So you can think of the mean value of a random variable as the point that balances the different values, that balances the different weights here. You can think of the probabilities as weights. So the mean value is like the balance point. Here we have another random variable. We have another random variable that has different values. Obviously, this variable is not the same as this variable. Here we have 2 and maybe 2.5 and maybe 2.7 and maybe 6.7 here and 8 and 8.7 and 10. This variable has different values like 5 and maybe 5.5 and so on. So the values of the variable x are different and the probabilities are also different. So this variable is not the same as this variable. However, when we calculate the mean, by coincidence, the mean, the average of these values is the same as the average of these values. This could be the case. So this variable and this variable have the same balance point, let's say 6.3 or something like that. So we have the same mean, which means the same balance point. However, we are still having two different variables. What is different for these variables? Think about the variance. I'm still not done, sorry, I'm still not done with how we can calculate the variance, but at least conceptual here. The variance represents the differences between the variable values, the average distance, the average difference between the first value and the mean, the second value and the mean, and so on. Here, the variance is the average difference between the first value and the mean, the second value and the mean. So for this variable and for this variable, which variance do you expect to be higher than the other? Here, the variable values are different from each other. Here, the variable values are closer to each other. So for this random variable, the variance is larger, and for this variable, the variance is smaller. So again, the take-home message here is that the variance represents how different are the different x values, how scattered are the different x values. Here, it's really scattered far away from each other, and here they're scattered closer to each other, and this is what the variance means. Expected value of the different variable values minus the mean squared. So that we can reach a nice formula that we can use in doing the calculations. Let's do a small proof to get the equivalent form. This is the equivalent form of this is the original definition of the variance. This is an equivalent form which is easier to use in the calculations. It's very easy to see, and let's do this proof together. So the variance of x or sigma square is defined as the expected value, open bracket, inside we have x minus mu square. So to get the equivalent form, let's work out this square. What is x minus mu square? So still the expected value is outside the bracket, so it's expected average of all this, what we see inside. But let's work out the square. X minus mu all square is x square minus 2 mu x plus mu square. Now let's apply the expected value to each one of these terms. But before we do that, let's keep in mind the following. Let's notice the following. X is a variable, but mu is a number, right? What's the expected value of a number? It is just the number itself. What is the average value of 5? You have just one value of 5. What's the average of 5? It is just 5 itself. Let's keep this in mind and apply the expected to each term. So in the first term, we have the expected of x square. 2 mu is a constant, so we take it outside, times the expected of x. So 2 mu times the expected of x plus the expected of mu square. Mu square is a value, is a number, a numeric value, and the expected of it is just mu square itself. So in total, this definition is equivalent to expected of x square minus 2 mu times the expected of x plus mu square. To simplify this expression, let's remember the following. What was the expected value of x? What did we call the expected value of x? It's also called mu here. So in the definition, instead of writing mu, I could have written expected value of x, but if we write mu, it becomes nice and concise and clean. However, we can remove the expected value of x once we apply the expectation. On this x, we get expected value of x, but this expected value of x is also called mu. So the middle term is minus 2 mu times mu minus 2 mu square. Let me rewrite this equation. Expected value of x square as it is, minus 2 mu square plus mu square as it is. Now we can combine these two terms. Minus 2 mu square plus mu square is minus mu square. Do you see this equivalent form? So the variance of x can be calculated as the expected of x square minus mu square. What's the expected of x square? It's the average value of the square of the variable. How can we calculate that? What was the expected of x? It's the summation of x times f of x, right? Expected of x square is also the summation of x square times f of x. Finally, once we do the summation, we have to subtract mu square. Mu is the expected value that we should calculate in a separate step. So this is basically what you see here. So the variance of x has a basic fundamental definition. We talked about it enough, but this definition is equivalent to the summation of x squared times the probabilities f of x, and then at the end minus mu square. Mu here is calculated using this step. So if you want to calculate the variance, we should calculate the mean, and then we calculate the variance in which the mean appears, but we have to square it. The best thing to do is to see an example here in which we do the calculation explicitly together. For this example that we have seen, so we have 4 communication messages, and x denotes the number of errors, and the probabilities are given. If you put everything together, x is 0 or 1 or 2 or 3 or 4. We talked about that, and these probabilities are just given. We did not have to calculate anything. The probabilities are just given, so the probability that x is 0 is 0.6561, and so on. The probability that x is 4 is 0.0001. What is the question? The question is find the expected value of x and find the variance of x. These are the final answer, but let's do the calculation together. How do we get the expected value of x? From the definition, summation x times f of x. How did we do that? 0 times probability plus 1 times probability plus 2 times probability, and so on. So 0 times the probability plus 1 times the probability plus 2 times the probability plus 3 times the probability plus 4 times the probability, multiplying each term and then adding up all the terms, you can verify that the answer is 0.4. So what is this 0.4? It's the mean value of our random variable. Yes, our random variable, which meant the number of errors in a communication message, and that variable x itself, the variable x itself, is either 0 or 1 or 2 or 3 or 4, but on average, it has a value 0.4. As you notice, it's somewhere between 0 and 1, simply because these have the highest probabilities. These probabilities are really small, 0.048, 0.00, 0.001, and so on. So the average value was 0.4. Now, how can we calculate the variance? What was the definition of the variance again? The definition of the variance, expected value of x squared here. This is better. Expected value of x squared minus mu squared. So let's write this down. The variance of x is the summation of x squared times f of x minus mu squared. Again, this is the expected value of x squared. How do we get this term? Very simple to the expected. In the expected value, it was 0 times probability plus 1 times probability. In the expected value of x squared, it is simply 0 squared times the probability plus 1 squared times the probability. So very similar to this, but the x values just have a square on top. So 0 squared times the probability plus 1 squared times the probability. We forgot the 2 here. This is a 2, sorry, this is a 2. 2 squared times the probability plus 3 squared times the probability 0.0036, finally plus 4 squared times the probability 0.0001. We're not done. Once we have this term, we have to subtract mu square. What was mu? We got it in the first step, 0.4, so we have to subtract 0.4 square. If you calculate all these terms, add them up, and then subtract 0.4 square, the answer is 0.36. So for this random variable, the mean value or average value or expected value was 0.4 and the variance was 0.36. Okay, if the question says what is the standard deviation for this random variable? To get the standard deviation, we have to get the variance. The variance is sigma square. So to get the the variance is sigma square. To get sigma itself, the standard deviation, we just need to calculate the square root of this, which would be 0.6. Let's move to another example, and then we will be almost done with this lecture here. The next example, it says the number of messages sent per hour over a computer network has the following distribution. So we observe a computer network like our university's computer network. It was observed that during 1 hour, the number of messages, the number of messages that we call X is either 10 or 11 or 12 or 13 or 14 or 15. So we just noticed that during an hour, the number of messages sent over the network, which we call X, this is our random variable, is 10 or 11 or 12 or 13 or 14 or 15, and each one of them having a probability which is given in the question. This is our random variable. So our random variable X, we can also put it vertically, it does not make a difference. X is equal to 10 or 11 or 12 or 13 or 14 or 15 with the given probabilities, and we just need to calculate the expected value and the variance. How do we calculate the expected value? Summation x f of x, so 10 times 0.08 plus 11 times probability plus 12 times probability and so on. So we add up all the terms, value times probability plus the next value times probability until the end, 15 times 0.07, and the answer is 12.5. So for these numbers, for this specific example, the average number of messages that are sent over this computer network during an hour is 12.5. On average, 12.5 messages are sent during 1 hour. What is the variance? We need to calculate the variance and the standard deviation. How do we calculate the variance? Variance, again, expected value of x squared minus mu squared. So we start with 10 squared times probability plus 11 squared times probability plus and so on until 15 squared times probability. But after all this, we have to subtract mu square. Mu was calculated, it's the same as the expected of x, 12.5. So at the end, we have to subtract 12.5 squared. Don't forget that. It's a famous mistake. Sometimes you forget it. If you have a question in which you want to calculate the variance, you just get the summation and that's it. No, we have to subtract mu square, which is 1.85 in this example. If in the example we wanted the standard deviation sigma, it is just the square root of the variance, square root of 1.85, which happens to be 1.36. Okay, we just have one definition, which is an extension of the expected value here. Let me go back to the definition of the expected value. What was the definition of the expected value of x? The summation over all possible x values. What are we adding up? X times f of x. So x value times probability and so on. And we have done it in a couple of examples. X value times probability plus x value times probability. Okay, let's notice something interesting as well. When we calculated the variance, as part of calculating the variance, we needed the expected value of x squared. The expected value of x squared is not the same as the expected of x. Expected of x means the average value for the x variable, but expected of x squared means the average value of the square of the variable. To calculate this term, it was the summation of x squared times the probability is f of x. So it's an extension of the expected value. Expected value summation x times probability, but expected of x squared was summation x squared times probability. So it would be 1 square times probability plus 2 square times probability and so on. Now imagine for any reason I wanted the expected value of x cube. What's the average of the cube value of the variable? How do we get the expected of x cube? Simply, it's the summation of x cube times f of x times the probabilities. So it would be 1 to the power of 3 times 1 over 6 plus 2 to the power of 3 times 1 over 6 and so on. So as you notice, depending on what expected value we want, if it's x squared or x cubed, it appears in the summation. but multiplied by the probability function f of x, which is never squared. So it's always as it is. These are the weights. However, it's multiplied by whatever function we need to calculate the expected value for. We can put all this together in this concept, the expected value of a function of a discrete random variable. So not the expected of the variable itself, the expected of any general function of the random variable. So x is a random variable that has a probability mass function f of x. So this f of x represents the probabilities. What we want is the expected value of h of x. H of x is any other function on the variable x. What is the expected value of h of x? Like the expected of x squared or x cubed or square root of x and so on. How do we calculate the expected of the function h of x? Again, it's the summation of the function values h of x multiplied by the probabilities. It's just a straightforward extension to this discussion in which I covered expected value of x squared, and then I also talked verbally about how to get the expected of x cubed and so on. In general, the expected value of any function of x is the summation over all x values of h of x times the probabilities f of x. Like for example, these are some examples. X is a random variable that has a probability function f of x. What's the expected value of the root of the variable? It would be a summation over all values of x, square root of x times f of x. Like for this example here, what's the expected of root x? Square root of 0 times the probability plus square root of 1 times probability plus square root of 2 times probability and so on. As another example, what's the expected value of x cubed? Summation over all values of x cubed times f of x. Finally, what's the expected value of 1 over x? What's the expected value of the reciprocal of the variable? Make no mistake, you cannot get the expected value of x and then just get the reciprocal. So the expectation of 1 over x is not equal to 1 over the expectation of x. That's not true, but the expected of 1 over x can only be calculated by applying this formula. 1 over x is just a function of the variable, so it would be a summation, the summation over all x values, but we add up 1 over x times f of x. Let's try to see an example for which we can obtain this. We cannot do that here because we have 0. 1 over 0 is just infinity, so the expected value of 1 over x is infinity regardless of the other terms. But let's look at another meaningful example here. In this example, what's the expected of 1 over x? It would be 1 over 1 times 1 over 6 plus 1 over 2 times 1 over 6 plus 1 over 3 times 1 over 6 and so on. So what we see here is really called the expected value of a function of a random variable. And this is the generalization I wanted to talk to you about, and we will continue with the next lecture, inshallah. Assalamu alaikum wa rahmatullahi.